Hello friends, welcome to my YouTube channel. Today we will see the example of periodic heat flow. Periodic heat flow, as the cycle is repetitive, it can be described as a periodic heat flow. Many industrial applications such as steam generation in a boiler or air cooling in the coil of air conditioner can be modeled as a two-dimensional periodic heat flow. And the system that is modeled is a bank of tube containing flowing fluid at one temperature that is immersed in a second fluid in a cross flow at a different temperature. Both fluid are water and the flow is classified as a laminar and steady with a Reynolds number of 100. The mass flow rate of the cross flow is known and the model is used to predict the flow and temperature field that result from the convective heat transfer. Due to the symmetricity of the tube bank and the periodicity of the flow inherent in the tube bank geometry, only a portion of geometry will be modeled. So now you can see we have modeled only the half portion of the tube bank, and this will be our symmetric plane from the bottom left and right side, and at top left and right side, that will be our symmetric plane. As a boundary condition, they have given us bulk temperature, that is 350 Kelvin, and the mass flow rate, that is 0.06 kg per second, and temperature wall is given 450. This is our tube wall. So we have used the rectangle tube for this example. As I mentioned, that we have the boundary condition where we have the water properties, and the bulk temperature is given 350 top tube, 450 Kelvin, bottom tube 450 Kelvin, and mass flow rate is 0.06 kg per second. Reynolds number is given. Based on that Reynolds number, we can calculate, and we can call as a laminar flow. So let's get start with the Ansys Fluent. First, call the geometry. I have created geometry in Creo. It is a two-dimensional geometry. Just import geometry. And right click and go to the design modular. Preview seen that when we open the geometry, we define the name selections like inlet, outlet, wall in the geometry modular. But we can also define this inlet, outlet in meshing. So this time we will see what is the process for same. So in design modular we will not define anything, we will just generate and we will call the geometry and we will see the geometry. So this is our tube bank geometry half portion, and now you can see here we have the part body, that is the square section. So it is a two-dimensional. If I rotate this, now you can see it is just a surface. So here we will not define anything like inlet and outlet and wall. We will define in the mesh module. So just save it. I will say on my local drive. we will call mesh module and we will attach to the geometry. Double click on geometry. Sometimes it happens that we forgot to define the inlet outlet in geometry, so in that conditions you can also define at a, on a mesh module. Meshing is starting, it will take time. Our process is same, means we have to select the edge and then we have to right click and we have to define. Yeah, now we have the option of geometry and mesh, but before that we will go to the selection filter and we will select edge. Just select this edge and right click, create name selections. We'll call SYWM symmetry left top. Blank. I will copy this, then again select right side and create name selections. Yes, symmetry right top blank. In same way we will select bottom side, symmetry left bottom blank, and this one also. Symmetry right bottom blank. Okay, then this is our inlet. Sorry, just select and create namespace inlet, and this is our outflow. And now we have to select wall, so we'll select the geometry of the square to blank and we'll say wall top, and we'll select bottom side of blank, wall bottom. So now you can see we have the symmetric top blank left right, symmetry left bottom blank, symmetry right bottom blank, then we have inlet, outflow, wall top and wall bottom. So we have done with meshing and we have defined the name selections. So about meshing, just click on mesh and change the physics preference to CFD. Go to the sizing will on the curvature, proximity and curvature. Relevance center should be fine. And but here what we'll do, instead of the automatic mesh, we'll try with some methods, that is the meshing method. So insert method, and first we'll go with the triangles. So select the geometry or body, and one body is selected, and in the method you can see that we have the quadrilateral dominant, triangles and multi-zone. So we'll go with the triangles, and we'll just update the mesh. Now you can see we have the mesh, all triangles you can see, but we'll also define the boundary layer. So for that we'll use inflation, and we'll select geometry first, apply, and go to the boundary scoping method, that is geometry selections or name selections. So we can go by geometry or name selection, both we can do, but I will show you with the geometry selections. In the name selection you can directly select the wall top and wall bottom. So just click on edge. So on this edges we need a boundary layer, and now you can select. So now you can see we have selected 6 edges, and the maximum layer we are looking for 6 in the growth rate or increment of 1.2. and now just generate mesh. Now you can see, we'll zoom it little bit. So we have the 6 layer, 1 2 3 4 5 and 6. It is the increment of 1.2. Also we will refine the mesh, so we'll do the sizing. In that we'll select the face, and element size we'll go with the 2 mm, and just generate. Now you can see we have the fine mesh, and yeah, so then we have done with the meshing, and in next step we will set up the problem in a preprocessor. So I will save it before closing. Yeah, so next is we'll attach the Fluent to mesh, and we need to update the mesh again. Just right click or double click on setup. Here you can see it automatically detect our geometry as 2D, and we will take a double precisions, and rest of the option will keep as it is. Yeah, so next is we'll attach the fluent to mesh, and in next step we'll set up the problem in a preprocessor. So I will save it before closing. Yeah, so next is we'll attach the fluent to mesh, and in next step we'll set up the problem in a preprocessor. So I will save it before closing. So Yes, now in the boundary condition you can see we have the inlet, outflow, symmetry left, symmetry right, symmetry left top plank, symmetry right top plank, wall bottom and wall top. So here you can also check the information of the mesh on the console, where you will see the x coordinate, the geometry distance from for x coordinate is -2, 0.2 to minus 0.1 meter. Also we have the node information on each face of the geometry. Also we'll set the unit for a temperature, yeah, that is Kelvin. And so our solver is pressure based, and it is a steady state. And next step is to select the model. So first we have to on the energy equation, and as our flow is laminar, so we will not change the model, we will go with the viscous laminar. And before that we have to define the periodic zone. So just enter on the console and type mesh, enter, then modify dash zones, enter, then make periodic, enter. Here it asking the periodic zone. So we have this two inlet and outlet, so we have to find the number for that zone. So we'll go to the boundary conditions and we will see the ID of that inlet zone. So here now you can see at the moment it is velocity inlet and ID is 9, and for the outflow it's showing the ID 10. And so we will define here periodic zone 9, shadow zone will be the 10, that is our outflow, and rotational periodic no, right no, and enter. Create periodic zone, yes. Auto detect translation vector, yes. So it will computed translation deltas, and zone 10 deleted, that zone 10 that was our outflow. And now you can see in the display mesh, just unhide all the zones and select the inlet. Now you can see we have the two, one is our periodic zone, and this will be the shadow for that. So it was a ID 9 and for this ID 10. So again select all. So we have defined the periodic, and now you can see the change in the inlet. Earlier it was showing the velocity inlet, now it is showing the periodic. That we are that was we are looking actually. Okay, now the next step is to set the material, and as the problem description we need a water for that, and so we'll create a new from the Fluent database and just click on the list. Water. Copy. So we have the properties of water. Just create and close. Now we have the water liquid. In the sail zone condition, we have the square sections. Just edit, and instead of air, just change to the water. Okay. Next, we'll define the inlet boundary condition. That is our periodic conditions. So just click on the inlet, and instead of edit, just click on the periodic conditions. Now here you can see we will specify the mass flow in the direction X, and that is the 0.06, and the upstream bulk temperature is 350. So just say OK, do not update. And the next is we need to define the wall. So go to the wall. So symmetry left bottom blank left, and this wall bottom and wall top we need to define. So first we will go for the top and edit. So here you can see we have the thermal tab. In that you can define the temperature. So we need to define for top tube 450 and bottom is same 450. So here we will mention 450 Kelvin. Okay. Same for the wall bottom, and the thermal tab is temperature, and again we will define 450. Once it is done, then we will go to the solution. So here we have defined the boundary condition. Next step is the solutions. In the methods we will go with the coupled, and we will keep the rest of the option as it is. Just you can on the pseudo transient. These options enable the algorithm, pseudo transient algorithm, in the coupled pressure based solver, and this algorithm effectively add an unsteady turn to the solution equation in order to improve the stability and convergence behavior. So we have done with that, and in the control we will keep the value as it is. Then just go to the monitors and residuals. Here just on the plot and print to console, we'll keep the value as it is default. Energy equation is always 10 raised to minus 6, and for the continuity equation generally we keep the 10 raised to 3. Then click on the ensure the plot is enabled, and click OK to residual monitor. Next we need to initialize the solutions. So in the solution, go to the initializations. First we will do the hybrid initializations, because hybrid initialization method, and then we will patch with the upstream flow. The hybrid initialization method compute the initial flow field based on our inlet and outlet boundary condition. In this case, we have the periodic boundary conditions with a specified upstream bulk temperature, that is the 350 Kelvin, and you will patch that 350 Kelvin with temperatures to improve the convergence. So we'll initialize first. Once it is done, you can see hybrid initialization done. Then we will go to the patch, and here now you can see the temperature. Just click on temperature, put the value 350 Kelvin and select patch with our fluid domain, that is the square section of our tube, and say patch. Now close it. Once it is done, then we will save and we will write the file. To save, at every 3 iterations the file will write. Say OK. Now go to the run, and we'll define the number of iterations 350, and we'll check at what level of iteration the solution is converged, and just we'll calculate. It will take time. I will show you the plot, residual plot, and now you can see this pop-up message showing the iteration that is going to write at every 3 iterations. So it will take time, and now we have set the 350 iterations. Now it is 52, 53, and also you can see the continuity equation is going down below 10 raised to 3, and after that it will be a constant, and energy equations has to go or reach 10 raised to 6. So I will come back once the solution is completed. Hello friends, welcome back. Now you can see our calculation is done, calculation completed. In the console now you can also see solution is converted at 144 iterations. Now we'll go and we'll see the post-processing results, and in the graphics we'll go the contour, and first we'll see the contour for pressure. Just click on the field options, take the pressure and static pressure, go with the smooth, and here just say the display. Now you can see the difference between these coloring options. If I go with the bandit, now you can see, and if we go with the smooth. Okay, now we have to on all the our symmetric planes, and for that we need to go to the viewing and display options. So just close this and go to the viewing and view display options. Here you can see we have defined this 4 symmetric, top and bottom. So just select all and apply it, close. Now you can see we have the symmetry, and we have the complete geometry for same. Next is here you can see next we'll see the temperature contour, and for that we'll go to the contour again and just click on contour. Here we'll say the temperature contour, it is a field, and select temperature, static temperatures, and click on the display and just take the smooth options. And here now you can see the contour in a screen. It's showing a contour of static temperature, and the temperature increases in the fluid due to the heat transfer from the tubes. Now you can see this area, we have the maximum temperature, that is 450 Kelvin, and this area is having temperature 450 due to we have defined our boundary conditions, and the hotter fluid is confined to the near wall and wake region, while a narrow stream of cooler fluid, you can see this, is convected through the tube bank. Next we'll see the vector, contour vector, and you can just say the velocity, and here you can take the velocity and color by velocity magnitude, and just click on the display. You can go to the scale and make it double and display, and just zoom. Now you can see we have the flow, recirculating flow behind the tube. So this is our tube, and we have the recirculating flow behind the tube. Also the at initial condition also we have some circulating flow. Mostly this you can find around our boundary layer along the tube surface. Now we can plot some we'll plot the temperatures, and for that you can go to the plot in the monitors, the result, go to the or you can go to the setting up domain here, and we'll create a ISO surface to see the temperature plot, and we'll create a ISO surface, and for that you can just call the mesh for that to the x coordinate and compute. So we know the distance minus 0.2 to 0.1 meter, and in between we will create some 3 ISO surface, and we will plot the temperature. So here first we'll take the plot on 0.5, and we'll give the name x is equal to 0.05 meter, and just create it. Then next we will create on 7, we will give the name x is equal to 0.07 meter, create, and last is at 9, we can check x is equal to 0.09 meter. So we have created ISO surface. We'll define the plot, go to the plot, XY plot. In XY plot you can go to the, here we have to plot on y-axis, so this should be 1 and x should be 0, that is for our distance, and here we will change a temperature and static temperature. In direction vector, we'll select the created ISO surface, and now you can also write to the file or positions. In the axis you can in the curve you can change the pattern of three curves. For the first, we'll take the pattern dash line and the symbol star, and now you can apply. Now for next, we'll go with 2 dash and the symbol is star, multiplications, and the color is red. I will go for apply, and the next we'll go with the dotted lines and the symbol is plus and the color is green. For that we'll say apply. Once it is done, just select on the plot, and now you can see we have the plot for a static temperature versus positions, and we have these three curves. So now we have seen the problem of periodic heat flow. In this tutorial we have seen the periodic flow and heat transfer in a staggered tube bank were modeled in Ansys Fluent. The model was set up assuming a known mass flow through the tube bank and constant wall temperature. Due to the periodic nature of flow and symmetry of the geometry, only a small piece of the full geometry was modeled. In addition, the tube bank configuration lent itself to use of a hybrid mesh and quadrilateral cell around the tubes and triangles elsewhere. The periodic condition dialog box make it easy to run this type of model with a variety of operating condition. We can also check with different inlet or mass flow rate, and we have to check the flow field around the tube blank. Also we can change the Reynolds number and we will see the effect on the flow field around the tube blank. So I have done with this example. If you like this tutorial, so please press the like button and subscribe my channel. In next tutorial we will see the more example of the periodic heat flow. Thank you.